I mean, so it's a good question about the hypothesis testing stuff, particularly to do with confidence intervals as well. In this course, it's relatively straightforward on the basis that there are only two types of test, and we only look at them to do with means, right? Now, if you have looked at anything in sort of advanced statistics, I know your background is, it's a myriad of, you know, all these different tests, and there's different situations when you should apply the right test. To be honest with you, we break the rules a lot in this course because there's a lot of situations whereby you say, well, actually, that's not the best test to use. But for the sake of, you know, we call it the fundamentals of statistics, we kind of just look at the two, just for the sake of getting the idea, right? So, the two tests that you can use, first of all, well, okay, the two distributions that you can sample from, I should say. Can you remember them?
So the distributions would be normal?
Yeah, good. So they're normal shape, right? First one is the t distribution, and the next one is the z distribution. Okay. What's the difference between them?
The z is for when you're looking at bigger than x numbers of data, I guess. 30x.
Good, exactly.
30, yeah.
So it's to do with sample size, right?
Yeah,
So yeah.
Sorry.
That's all right. So n is greater than or equal to 30. Let's just do it for one sample for the moment. So for n greater than or equal to 30, if the answer to that question is no, what test do we know we could use immediately?
T.
Yeah, good. The t distribution. The idea is that the t distribution, it looks roughly the same as the z distribution. If I showed you those two distributions side by side, you'd be like, well, they're the same shape. What's the difference between the t and the z then in terms of the shape and in terms of the graph? So if I literally just draw them on the same graph, so if this is the z distribution, okay, so that's z. The t distribution would follow the same shape. However, we have this additional parameter with t distribution. Can you remember what it is?
Population standard deviation.
Oh, a bit more than that. In terms of the sample size.
Oh. Well, it depends on the degrees of freedom.
Perfect. Yeah, degrees of freedom, or DF for short, right? And the degrees of freedom is a function of the sample size, right? So the idea is that this t distribution will actually change in shape, or at least change in terms of what it looks like, according to the sample size, okay, according to these degrees of freedom. Do you remember what the degrees of freedom always is for this course?
N-1.
Yeah, perfect. So you just take however many things are in your sample and take away one from them. I think when we went through it, we had a brief discussion as to why. The idea is degrees of freedom is literally the most amount of things that are allowed to change before you know everything about the situation, right? So as an example, have I got a coin on me? No, I haven't got a coin. But let's imagine I had a coin in one of my hands, right? So at the moment, my sample size is 2. There's 2 different places that the coin could be. If I show you one of my hands, then you know immediately everything about the system, right? So now nothing else is allowed to change. So in other words, the degrees of freedom in this case is 1, because there's one thing that's allowed to change before you know everything about the system. So, okay, so degrees of freedom is a function of sample size. In terms of what it looks like though, it's a bit more flattened out, like so, okay? And the idea is that for low sample sizes, it will be a really, really flat curve. But as the sample size increases, you get the t distribution approaching what the z distribution looks like, all right? So as n, sample size, gets bigger, so I can say approaches infinity, gets bigger, then the t distribution should approach the z distribution anyway. Question, will it ever be exactly the same as the z distribution?
Don't know the influence of degrees of freedom at that point. I guess it's just depends if you say it's significant or not.
Yeah. So the truthful answer is no. The t distribution will never be exactly the same. It will never follow it exactly. However, we just say that for sample sizes above 30, right? So for degrees of freedom which are 30 or less, we can, sorry, 30 or more, we can say that the t distribution and the z distribution are so close to each other, we really can't tell the difference from each other, right? They're so different, they're so close, they pretty much follow exactly the same curve as each other, so we don't really, you know, we're fine just to use the z distribution in those reasons. Good. Now, this was not the only question that we asked ourselves. So, first of all, if n is greater than or equal to 30, if the answer to that question is no, we use the t distribution, right? So we've got that in the bag, right? Because clearly this curve looks nothing like that for low degrees of freedom. But what's the other question that we need to ask? Even if we do have a big enough sample size, what's the other question that we need to consider?
If I remember correctly, it's if we know the standard deviation of the sample size.
Not the sample.
I mean, because there's two of them, right? But if there's only one, it's going to be one, I guess.
Right, so it is to do with standard deviation,
Yeah,
but it's not standard deviation of the sample, it's standard deviation of the population. Yeah. So we call that sigma, remember the notation, S is sample, the Greek letter S is population. So do we know the population standard deviation, basically? And if the answer to that question is still no, so we may have a big enough sample size, right? We say, yep, we've got big enough sample size, now do we know what the population standard deviation is? If the answer to that question is still no, then we still have to use the t distribution. It's a kind of a penalty, if you like, because we don't really have an idea of how the distribution should be spread at the population level. So it's more kind of, it's just more conservative to use the t distribution. However, if the answer to both those questions is yes, that is when we can use the z distribution. Okay? So only if we know that the sample size is big enough and we know what the population standard deviation is doing, in other words, we know roughly what the shape of the curve is doing, that's the only time we can use the z distribution. Now, as I've said to you, if you understand what's going on, there are some situations whereby if you can justify it, you'll find to use the z distribution. This is the art of statistics. It's about looking at the situation which is in front of you and thinking dynamically, rather than just following like an algorithm or a rule. As long as you can justify which test you want to use, that is fine. So for instance, in the last exam, which was sat about 2 or 3 weeks ago by the people that started in September, I gave them a situation whereby they had sample sizes, it was 2 samples, but there were sample sizes which were bigger than or equal to 30 in both cases, but I didn't tell them what the population standard deviation was. I told them what the sample standard deviation was. Now you would have still got 4 marks if you went for the z distribution, as long as you justified why. So basically, it was because the sample sizes that I gave them were so big. They were like 100 and 150, I think, right? So it was way bigger than 30. So as long as they put this justification down and said, well, actually, the sample sizes in this case are so big that we can pretty much use the z distribution because the t distribution approaches the z. Now, if they didn't give that justification, they didn't get the marks, or at least those marks for that sort of justification of the test. But it is totally fine to use the z distribution in certain cases, right? So as long as you can justify, it's fine, right? This is just one way that you can use to justify it, but there are other ways as well, okay? Now, that's obviously the first thing that you need to understand, you know, which distribution do you need to sample from. In terms of what tests we can do, there are only 2, and they're all based around the mean, okay? So in this course, we only ever look at hypothesis tests for means, okay? So for the population mean. So I'm going to use mu for the population mean. So the first type of test that we can do is what's known as a one sample. In other words, I want to establish, does a particular type of, I don't know, chocolate bar weigh 50 grams, okay? So obviously we can't go out and measure every single chocolate bar and take the average of the entire population, so we take a sample, okay? So it's a one sample test, and we want to establish, is mu equal to 50 grams? Is the population mean equal to 50 grams based on a sample data, okay? So in this case, with a one sample test, we are looking at whether the mean is equal to a particular value, okay? Okay, so in the other situation we could have is a two sample. Now in this instance, we're less interested in what the means actually are and more interested in whether there is a difference between them, okay? So literally we are looking for a difference in the means. Okay, so for example, the difference in the means could be equal to 2 or 3 or 4 or 0 or whatever value you like. Okay, so that's the difference between the two different tests that we could have. A one sample test simply just says, okay, is the population mean equal to this value? Two sample test looks for a difference in those populations. And to be honest with you, those are the only two tests that we look at. There are other tests, as I'm sure you're aware, there's ANOVAs and all these sort of chi-squared tests and tests for correlation and bits and bobs like that. But in the sake of this argument, then we are fine just to use either t distribution or z distribution to sample from, and yeah, one sample and two sample, okay, for the mean. Is that okay? Cool. So yeah, obviously in this case, if we have a two sample, so this is the test for a one sample or a justification for a one sample. If we wanted to do a justification for a two sample, how would we change these two questions?
I guess the ends for both samples.
Yes. So in other words, we need the sample size of sample 1 needs to be bigger than or equal to 30, and so it's not an or situation, it needs to both be bigger than or equal to 30. Okay, so that's obviously the first question we ask. And the second question we ask,
deviations of all populations?
yeah, good. So in other words, we need to know the population standard deviations for both. And just like before, if the answer to either of those questions is no, so if the answer to this question is no, we use a t distribution. And if the answer to this question is no, we also use the t distribution. If the answer to both of those questions is yes, that's when we use the z. But again, that's just one way that you can justify it. You can absolutely try and base it around the central limit theorem argument, right? So yeah, I guess we call this the central limit theorem. So I'm just kind of give you one way that you can try and justify which test you want to use. This is not by any means a hard and fast rule. Again, you've got to think about the data which is in front of you and make a decision based off that. And obviously just one final thing, if we're dealing with two samples and we end up using a t distribution, the degrees of freedom is not just going to be n-1 anymore. What's the degrees of freedom going to be in this case? Yeah, so we have to add the 2 degrees of freedom to each other, or add the 2 sample sizes to each other and take away 2. Yeah. The way which you can think about that, or the way which I think about it at least, is it's literally just n1 minus 1 added to n2 minus 1. So the 2 degrees of freedom added to each other. All right.